So JM6. So yeah. So in the lecture and in the book, I make this point that the formula for the Jacobian matrix is simple, right? It's made up of just a bunch of partial derivatives, and you can compute partial derivatives in lots of cases. But just because you can actually assemble a matrix that looks like the Jacobian matrix doesn't mean that it actually is a Jacobian and that the function's differentiable and that all this good stuff happens. So in fact, I claim that this function here is not differentiable. And we talk about that a ways back. Let me just go back to show you what to read here. So yeah, so this, here it is. That's that function, right? And if you sort of make your way through this example, what you find is that this function is not directional linear. Right, so I'm going to let you guys read this example. Basically, this example is about studying this function that looked like this, which you remember we did this. You look at it from different angles, and it's like all the cross sections of this look perfectly normal, and yet you can see there's some weird sort of fold corner. Something terribly wrong is going on there. For example, there is no tangent plane at that point. Just forget about it. Right? So wildly bad function. Nevertheless, all of the directional derivatives are easy to compute. No problem. There you go. It's directionally differentiable. It's just not directionally linear.
Because they equal 0?
I'm sorry?
Because they equal 0?
No, because it's... well, I mean, this was just one way. This is how I happen to show that it was not directionally linear, is that you have two different directions here where the directional derivatives are both 0, and yet it's not identically 0. If it were linear, and if it were 0 that way and 0 this way, it would have to be 0 everywhere. But it isn't. Right? The directional derivatives it's just not linear. It doesn't have this linearity property. Yeah. Now, if it were 0, if this was 0, if the directional derivatives really were 0 in every direction that you look, then yeah, it would be directional linear. But the point is it's not. Yeah, yes?
I don't understand why the directional derivative of that second vector is equal to 0.
Why is this equal to 0?
Yeah.
Yeah. Okay, so if you look at this, let me draw a picture. So let's look at that vector. So let's see, 1/2 and then root 3 over 2. So that's a vector about like this. In fact, that's a vector where theta is pi over 3, right? And we have a formula here if, up here, if you want to take the directional derivative, this is all at the origin, of course, where you're going in the direction of some vector. Well, here's a formula for it. Just take the length of your vector and multiply by sine of 3 theta. Well, if theta is pi over 3, then we're looking at sine of pi, which is 0.
Oh.
And that's why we get a 0 here.
Right.
Yeah. It's kind of weird.
I just missed the 3.
No, yeah, no worries. Yeah, the 3 is very important. Yep. That's the same 3 from here. Exactly. Okay, so this is the punchline. Now, I encourage you guys to read through this example, and the calculations that go into actually computing this come from this discussion of how you evaluate this function off of this formula here. So moving back to the problem now, though. Here it is. Looking at the problem, we're looking at this function, and we want to decide if the following argument is valid. Well, the argument says, okay, I want to compute this directional derivative. We compute directional derivatives with Jacobian times the vector, but wait a minute, if you're going to use the Jacobian to compute directional derivatives, you're asserting that this function is differentiable. Well, I claim it's not differentiable. In fact, it's not even directional linear, much less is it differentiable. Remember, we have this hierarchy of regularity conditions. We've shown the function in question, it's not even directional linear. It's directionally differentiable. The function we're looking at has these two properties. It is directionally differentiable. It is partial differentiable. You can compute these things. But it just doesn't have these nice properties here. Since it's not directional linear, it definitely can't be differentiable. And differentiability is what you use to define the Jacobian matrix. So we have a function that only has these properties, but we're pretending like it's got this property. And that's illegal. That's the flaw in the argument. Let me come back down to the problem. In this step right here, we're assuming the function is differentiable. It isn't. So this is just garbage. You know, assembling these partial derivatives like so to make a Jacobian matrix as if the Jacobian matrix has anything to do with these directional derivatives is just wrong. And that's why we get a wildly wrong answer. I mean, in fact, you can check. So the next part of the problem says, actually, let's compute the correct value of this directional derivative. Well, we can compute that correct value by going back to this example. We have a formula for how to compute directional derivatives. Here it is. Just figure out what's the angle. Compute sine of 3 theta. Multiply by the length of your velocity vector. This is all stuff that you can do for that velocity vector that was given. Come back down here. Whoops, too far, sorry. For this vector 1, 2, you can compute the angle, you can compute sine of 3 theta, you can compute the length of that vector, multiply. This is totally computable, and it will not equal to -2. So the purpose of this problem is to show you that this idea, I mean, again, this is a super sloppy idea. I computed the partial with respect to x, I computed the partial with respect to y, and then I just figured, oh, that means this is the Jacobian matrix. Nope. This is only the Jacobian matrix if the function's differentiable, and this one is not. This is why it's important to check, to assert that the function's differentiable, to know why the function's differentiable, because it's only if the function's differentiable that this kind of an argument is valid. Does that make sense? Anybody have any questions about this problem? Okay. Okay, great. Let me stop the recording.